In this video, we're going to try and understand why related rates work. I'm assuming you know how to do related rates problems. You just don't understand why it works. So let's look at this problem. We've seen this problem before. You've got an oil tanker here. You've got an oil tanker here, and it's leaking oil. It's leaking oil. So the area of this circle will expand with respect to time. So as time goes on, so your oil tanker is here. As time goes on, it's leaking oil. So the area will just get bigger and bigger. And you want to know how fast it's growing with respect to time. So you really want to know dr by dt. So to solve this, you would look for something that connects everything, and it is this formula that connects everything. So once you've got your formula, then all of a sudden, when it comes to related rates problems, all of a sudden you differentiate it. It takes you to here, and then you would just plug. You want to know this. You know this will be given to you in a problem. You know the radius at a given time, and then it's blah blah blah. You can work this out. But so normally with related rates problem, you would start out with something that connects everything, and then all of a sudden you differentiate it, and then everything seems to work. But the problem is you don't understand why it works. Why is it that when you differentiate this with respect to time, and then differentiate this with respect to time, and then blah blah blah, and then all of a sudden it works? We're going to try and understand why that's the case. So for example, another one is this one here. We've seen this problem before. You're filling up this conical tank with water. The problem will give you a volume as time goes on. So you will be given dV by dt, and then up to a certain height, which will be given to you. You want to know how fast the water level is rising, because when you fill it, when this is constant, when you're filling it up, it will fill up really fast because the volume is really small here. But then as time goes on, it will slow down because the volume here is much bigger than what's down here. So you want to know, in effect, you want to know dH by dt. So you would find something that connects everything. And for this case, by the way, I'm assuming you can do this problem. We've done this problem before. You would find something that connects everything, and it turns out to be this formula. This formula connects everything, but you don't want the h here. But when it comes to a cone, you're always going to have a radius, the radius of r, the radius of 5, and this height is 10. This height is 10. The ratio is blah blah blah. We've done this before, so I'm assuming you can do this. So h turns out to be 2r, and then you would put this into the h here, tidy this up. That will then take you to here. So now the formula is all in terms of r. There's no h in here, so it's all in terms of r. So from here you would then differentiate it with respect to time. So differentiate this with respect to time. So differentiate this with respect to time. That will then give you this, and then differentiate this. That will then give you this thing here. But because r is a function of time, then all of a sudden you stick dr by dt, and then all of a sudden it works nicely. Now you don't understand why it works nicely. So in this video we're going to try and understand why it is that you can just stick dr by dt and dv by dt, and all of a sudden it works neatly. And another example is this. The rocket is, you're a cameraman or woman here. You're trying to film a rocket launch. This rocket here, it has reached a height of 400 meters, and it's traveling at an unrealistic speed of 7 meters per second. Let's just imagine it to be like this. So you want to know, but at this precise moment in time when it's 400 meters, you want to know how fast you need to rotate your camera. So for this situation, you would look for something that connects everything. Well, if you look at this, it is tan that connects everything. It is tan that connects everything. You're going to call this h. You want to know the angular speed here. So in effect, you want to know d theta by dt, and this here is actually, well, h is the height. This is a speed in terms of height. So this thing here will be dH by dt. So you would look for something that connects everything. It turns out to be this, and then And then because as time goes on, h is a function of time. The angle here varies as time goes on, so theta is a function of time. So whenever you differentiate it, h, you need to stick dh by dt. And then when you come to differentiate it, because theta is a function of time, you need to stick d theta by dt. So anyway, back to here, you would find something that connects everything, and it turns out to be this formula that connects everything. So you would differentiate this, that would then give you this, and then because theta is a function of time, you would stick d theta by dt. And then this thing here, let's just imagine it as like this, 1 over this. Let's just imagine it as this. So when you come to differentiate it, it would be your constant here. It would be your constant here because the height varies with time, because h is a function of time in our scenario. By the way, this is not a function of time, so it's a constant. Because h is a function of time, we need to stick dh by dt. Now, once we're here, if you differentiate it, it will then give you this, and then all you need to do now is just plug this in. You want to know this thing here. You want to know the angular speed, d theta by dt. This is actually, well, h is the height, and it's a change. Well, this thing here is actually dh by dt. So you can put this into dh by dt. And then at this precise moment in time, when it's at a height of 400, then tan theta will be 400 over 1000, will be over 1000, and this is tan squared. So you would square this, blah blah. You would plug this into here. You want to know this, you know this, and then it's blah blah blah. You can work backwards to find out d theta. The point is that once you're here, we normally just blindly compute this and then jump to this stage, and then we want to know this, so we plug everything into here and plug in everything into here, and then we can work out what we want to know. But the thing is, we blindly do it, but we don't fully understand why it works. So in the next video, we're going to try and understand why that's the case. Okay.